So I'm Chris Richardson, and along with Dimitri, we organize, or attempt to organize, this JUG. It didn't get organized last month, but going forward, trying to actually get back to our regular monthly schedule. Kind of want to thank Robert Half for providing the space. I want to thank Cloudera for providing the pizza, which is cool. But actually, going forward, we actually do need a new pizza sponsor. So if anyone wants a great opportunity to get their name in front of, we have, I think, 850 members of the JUG now. It's kind of a good marketing opportunity. And I also want to thank New Relic, who are sponsoring the video recording for tonight. If any of you came to the January and I think February meetings, we actually videoed those, but then I kind of sat on the recordings, and then I had to ask Matt, who's doing the videos, to actually pull them out of archives again. So they are now posted on YouTube, and I will send out an announcement in the next couple of days. So yeah, Cloudera, Robert Half, New Relic, all help to make this JUG possible. All right, so let's get started. So there's sort of actually 3 different talks tonight. So one of them is this, which is on basically a bunch of distributed systems related frameworks, tools, goodies that I've been using directly or indirectly over the past year or so. And then after that, actually, I'm going to give a talk on Docker, which I know is one of the most popular topics for tonight. And then Dimitri's going to talk about Mesos, Marathon, Kronos. Anything else?
Also Zookeeper, Eureka, Docker, Spring Boot.
Awesome. So it's an entire evening of just awesome technologies. All right. So yeah, so if this works. So yeah, as I mentioned, a bunch of the distributed system sort of building blocks. A bit about me. So I got my start programming Lisp back in the 80s. Eventually ended up programming in Java, wrote the book Pojos in Action, which was like a long time ago now. 2006 it came out. It is still selling 1 or 2 copies a quarter for some bizarre reason. And then, thanks to this JUG, actually, back in 2006, I heard about this obscure service called EC2, back in the very early days. Was it in this room? Yep. It was upstairs. Totally blew my mind, just the notion that you could go rent servers for, up to 20 servers for 10 cents an hour, right? And, we all know where sort of EC2 went. And along the way, I got so excited, I ultimately created a startup called Cloud Foundry, which was a Java PaaS for EC2 that got acquired by SpringSource right before SpringSource got acquired by VMware. So then I had been there for four and a bit years until about 18 months ago. And now sort of trying to get going on my own thing and building a platform for writing what you could call reactive microservices, just to combine 2 very hot buzzwords into one description. And so some of I got some source code on GitHub. Actually, the second link is basically the code that I'm talking about in the Docker presentation. But I also have the website microservices.io, which is a collection of patterns that can guide you when deciding whether or not to use microservices, and if you do, kind of resolve some of the design issues that you have to address. So anyway, here's the agenda. So really just going to talk about 3 things. Zookeeper, which is kind of a foundational technology that just crops up everywhere in a whole bunch of open source projects. Helix, which is a somewhat obscure but very useful project that's actually built on top of Zookeeper. And then Kafka, that's sort of this super cool, hot messaging, highly scalable messaging infrastructure. So, okay, so let's look at Zookeeper. So, I pulled this off the website. So it's this open source, it's Apache, right? So it's open source. And basically, it's this service for dealing with configuration and synchronization and coordination, and also kind of naming service for just large-scale distributed systems. And I think it was part of Hadoop originally, though it's sort of become an independent project. So if you think, it's interesting, like most of the systems I've built over the years have sort of been distributed, but very much in a sort of degenerate kind of way, right? You just run multiple copies behind a load balancer, and you have request level parallelism, and you're just serving up web pages or handling REST APIs, and maybe you're talking to a database backend, possibly a message broker. So that's kind of a distributed system, but not so much, right? But once you start building more complex architectures, these days if you're building a microservice architecture, then, or if you're building some lower level infrastructure components, then there's sort of a whole bunch of different problems that you have to solve, right? And services that you need. So like, for instance, you need a naming service that lets you look up a thing by name. So if you want to talk to a service, you have to consult a naming service to find the host and the IP and ports of all of the different service instances, right? So obviously, that's like a mission critical, highly available part of your system. Kind of has to work reliably, and that's just one of the things that Zookeeper can do. Another example of sort of thing you might have to build is implement some notion of group membership. So if you have a distributed cache, for example, I think say cache might do this. The members of the cache have to communicate and coordinate, right? Possibly just like sending cache invalidation messages when a cache entry is updated. So now, but the problem you have there, of course, is that these members of this cluster, which could be changing size dynamically, they have to know about one another. So you end up with this group membership problem. And I think way back there was like technology like JGroups, right, which relied on multicast. But sort of multicast, that's kind of problematic, 'cause as far as I can remember, it still doesn't work on EC2, right? So sort of those traditional kinds of technologies don't work. So once again, Zookeeper's good at doing group membership. Another really interesting use case is leader election, right, where you have a cluster of n servers, one of which has to be nominated the master, right, has to be kind of in charge. And a great example of that is with master-slave replication, right? Or with MySQL or MongoDB replica sets, you have n servers. They hold an election and make one of those servers the master, and that's where writes go. And then the slaves kind of just get the writes from the master. So it's a kind of very sort of elementary distributed systems algorithm that's good to implement with Zookeeper. And then there are other examples like distributed locking. For instance, you can imagine I think I've had to do this in the past where I've had a cluster of machines and only one of those machines could actually talk to a remote server, right? The actual terms of service with that remote server was like exactly one connection. And so you could implement it with sort of a leader election, but you could also think of it as a distributed lock scenario where only one server can actually claim that lock. And so Zookeeper can do that. And then, of course, queues sort of, you can actually use Zookeeper as a messaging, kind of a low bandwidth messaging infrastructure as well. So architecturally, it looks like this. You have a cluster of Zookeeper servers. They actually maintain the configuration database in memory, but at the same time, they make it durable by writing it to disk as well. So you have to configure Zookeeper with a data directory. And the as you might expect, the Zookeeper servers communicate amongst themselves, nominate a leader, so that's who the client sends the writes to, and then the leader replicates those updates to the followers, and there's this ZAB, it's like Zookeeper Atomic Broadcast Protocol, that I think it's quite sophisticated, but it ensures consistency across the cluster. It's kind of like with every write, they have to hold a sort of little election and agree on, yes, this write should be accepted and should cause an in-memory update. And so when you run Zookeeper, you need sort of, you know, in a realistic system, you have to run multiple copies, 3, 5, or more. Clients support for it in a whole bunch of different languages. It ships with C and Java, Perl, Python, apparently. But then there are Scala and Node clients. And basically, the client just connects to the cluster and actually establishes a session. And that session can survive TCP disconnects. And there's a session timeout. And the notion of session is quite important because it's sort of things when your session times out, data that you might have written to Zookeeper can actually expire at that point. And that's actually kind of the underlying mechanism that sort of triggers like group membership, right? So if a member of the group goes away, it disconnects, and then eventually the session times out and it gets removed from the group. Similarly with leader election as well, when the leader goes away, its session times out, and then that removes some data, which actually then goes and triggers an election. A little bit more about that in a minute. So the actual data model with Zookeeper is that it's sort of reminiscent of a like a Unix directory, right? It's hierarchical. It's a hierarchy of named Z nodes that actually look like paths. So the root is / and then foo under that would be /foo. But one thing where it's different is that not only do nodes have children, but they also have data as well. So you can store data at these non-leaf nodes. And as I mentioned, there's this notion of an ephemeral. You can either have persistent nodes that once you create them, once a client creates them, and when it disconnects, that node stays there until it's explicitly deleted. But you could also have ephemeral nodes that only last for as long as the session. So when the session times out because of a client disconnect, that node will actually be deleted. That's really, really, really important. And then the other thing that clients can do, they can actually watch nodes for changes. So when they can establish a watch on the data of a node or on the children of the node. So in the former case, if the data changes, the client gets notified saying this node's data has changed, and then it can go reread that the updated data, or it can watch the children, and if there's any change in the set of children of a node, it can get notified as well. And oh, the actual data, it's just binary.
What would you use it for?
Almost like anything, actually. So like, so suppose you're implementing a naming service, right? So imagine you have a service called foo, or the account service to make it more realistic, right? So then when an instance of the account service starts up, it will actually create an ephemeral node, child node, under the account service node, and that node's data will be the instance's host and IP address. That's sort of one kind of straightforward use case. But it can actually, I mean, like Helix, say, is just storing arbitrarily complex data. Like you actually look inside Zookeeper, you will see JSON structures describing this kind of the state of a Helix cluster. Zookeeper, as the Kafka rather, is actually storing all kinds of information about topics. So when Zookeeper, you publish to a topic, those topics are defined by Zookeeper data structures. So you can, it's just, anything and everything can get stuffed in there. So basic Zookeeper operations, you can create a node with some data, you can delete it, you can check whether it exists, you can read the data, you can write the data, and you can get the children. So it's sort of basic tree type operations. And as I mentioned, you can establish watches as well. And you just get callback to say, this thing, whatever you were watching has now changed. So I was sort of messing around with the command line, right? So I actually connected to Zookeeper, and I created a node called whose path was /CER, gave it the value X, and then I created a child node and gave it a value Y. And then I actually, in another shell, did a get on the foo node, and so it gave me the value X back. Well, it should have been Y. Oops. Yeah, I'd actually had foos and bars as the value, and it was kind of confusing to me, so I kind of edited it. But I did a watch on there as well, so it's sort of you can actually do a get with a watch keyword. And then I did a set over here, so oops, it said and baz. But then the other client got notified. Anyway, so other than the slightly incorrect values, you sort of get an idea of what kind of the fundamental structures. Oh yeah. So the other really interesting thing is so not only can you have nodes that are ephemeral, so they go away when the session that created them ceases to exist, but there's this notion of a sequential node. So you can think of a node having a counter, and when you create a sequential child of that node, the value of the counter is appended onto the name of the node, and then the counter is incremented. So that sort of causes you to just generate a sequence of uniquely named nodes where they end in 001, 002, 003. So this was, creating with a -s said sequential, creating with a -e said ephemeral. And so it created it, and the node I'm creating is baz, and so it just stuck 0001 on the end and gave it the value AA. And there's some use cases where that is useful. And then I actually just said, show me the children of the CER node, kind of LS. And I said, watch them, right? And then this session over here exited. The other session then got notified that the children had changed. And then when I did an LS on it, you see that the baz 0001 node went away. So kind of what's interesting about Zookeeper, and some people have criticized it, is that it's very sort of low level. Like if you go, what's the other one, etc. D. If you read the motive, the reason we created etc. D was because Zookeeper was just too primitive, and so you kind of have to, on top of Zookeeper, you need recipes that then kind of implement the actual algorithms that you need, whereas some other systems might actually give them to you much more directly. But it's very flexible. So here's an example of leader election, right? So we've got some service, and it's like my app, and created a node called my app election that's going to coordinate the selection of a leader. And the way that works is, so each service instance, when it starts up, first off, it generates a GUID, so in this case, GUID A, and then creates a sequential ephemeral node under the my app election. And then another one starts up, generates a GUID, gets a new, creates a new node. Third one starts up. And then the idea here is that, so if I'm server A and the node I created is GUID A, and the counter that's associated with that is the lowest value, which it is, right? It's 0, then I must be the leader, right? So it's basically the node that has the lowest counter value is actually the leader of this cluster. And the reason that it actually creates a GUID in there is there's a scenario where you can create a node, and the creation of the node can be successful, but you get a disconnect from the server before you get the response back, so you don't know whether you've created it or not, right? But if you use a GUID, if you get disconnected, you can actually tell whether the node that you had intended to create exists or not. So that's why you got a unique GUID instead of just some kind of constant prefix. But then what happens, right, is, the other thing you do, so because server A has the lowest numbered node, it's the leader. And then the other trick you play is that the node with the number n sets a watch on the node with the number n minus 1, right? So B watches the A node, and then C watches the B node. And the reason you want to do that is because if server A goes away, this is going to be the next leader because it has the lowest number, but it only has to just look at the current leader's node, and when it goes away, it can say, I'm the leader now. So that's kind of, it's a fairly simple algorithm, and it's sort of, you just implement it with a bunch of ephemeral nodes. Yeah?
So no one is watching server C or GUID C_2 because obviously it will not become a leader until everyone else dies out. But the data in Zookeeper, right? You should then have it replicated to make sure that if server C and corresponding node C just go away for some reason, right? You won't lose any data in Zookeeper cluster.
Well, the only data that's being stored here are the hosts and the ports of the corresponding servers. So if they go away, that data has no value anymore.
If you have your load balancer also tied to these nodes, but then you could direct some part of your traffic to the node that is not existent. Yeah,
well, okay, so that's. So there's sort of the other part of that, right, so this is purely for lead, so far this is leader election. The other thing that, if you had some sort of load balancer in front of this, it could actually watch these nodes. It could actually have a watch on the children. And so it knows that, about their comings and goings, basically. And so, that's sort of all tied into service discovery, but basically you could either overload this or actually have a separate tree off in Zookeeper that's then used for service discovery. But the interesting thing is, right, sessions have a timeout, so there is actually, for that duration of the timeout period, a server is gone, but Zookeeper hasn't agreed that it's gone yet, right? And I think there's a whole bunch of issues about session timeout duration, right? Because if the timeout is too short, the server could be disconnected and it might be doing some full GC or something. And then Zookeeper will just think that it's gone away when it really hasn't. But if the timeout is too long, then it delays the leader election, right? Which impacts the the availability of your system. All right, so Zookeeper is like this building, foundational building block. Netflix created this curator project that basically sits on top of Zookeeper, makes it easier to use, and implements a bunch of recipes for sort of common use cases, like I think leader election and so on. And then they also created Netflix Exhibitor that is like a supervisory process that you deploy on the same instance as Zookeeper to actually manage it, clean it up, and make sure that it's running and stuff like that. I think I played around with Curator, but I haven't actually used Exhibitor. But it seemed sort of handy. All right, so that's like a super quick overview of Zookeeper. Next thing I wanted to talk about briefly is Helix, which is actually basically a kind of effectively implements a cluster management recipe on top of Zookeeper. So it's kind of like just this kind of uber complex recipe that's useful. I actually use this in the product I'm building, though the actual project is sort of not that active, right? Like Zookeeper is used incredibly widely, and Helix, not so much. Like the meetup, Bay Area Helix meetup, almost went away because the organizer quit, and meetup, it was like one day from being deleted from meetup.com. But anyway, it's kind of useful. So sort of the big idea, right, with Helix is that, a typical distributed system, kind of you end up doing a couple of things, particularly when you're sort of dealing with data, right? One is partitioning. So database sharding. So you've got some kind of, resource pool of data. You actually divide it up into chunks, and you use some number of partitions, and you use, say, the primary key of a row to decide which partition that data belongs on. So that's one common dimension. And then the other thing you can do is replicate, right? Because machines go down, and if the only machine holding that partition went away, you've lost your data. So you kind of typically have like 3 replicas. So you sort of 2 dimensions, you partition and then you replicate. And then there's sort of kind of another dimension to it, is that these replicas, or the partitions, or the replicated partitions might themselves have some kind of state machine, right? So you think about master-slave replication. One of them is the master, and that's the one you write to, and the other ones are slaves, and they kind of replicate from the master. So you can kind of generalize that to a sort of state machine model. Concrete examples, right? MySQL master-slave replication, or MongoDB replica sets. N machines, one master, N slaves. If the master goes away, then, well, first off, you have to decide who's the master, so you need a leader election. Then you also have to re-elect if the master ever goes away. And a slightly more different scenario is with Cassandra and its scheme, right? So basically, the cluster consists of n nodes. The data consists of m partitions. And then there's actually r replicas of each of those partitions. And it doesn't have a master-slave model. Client can actually write to any one of the replicas, and the remaining replicas then either synchronously or asynchronously get updated. So someone has to take care of dynamically figuring out, well, I've got, m times r partition replicas, and how do I distribute them both sort of evenly, but also in a reliable way, right? You don't want to have 2 replicas on the same machine across all of those n nodes. So Helix supports this model where you have a cluster, it's n machines. There's actually 1 or more resources. So in kind of databases, effectively in sort of data, like in MySQL, there's only 1 resource, just this big pool of data, kind of. But Helix supports multiple resources. Then the resources are partitioned in replicas. Each resource can then have this state machine like master-slave replication. And just Helix just takes care, you kind of define the cluster, define the state machine, and Helix just takes care of it and tells the machines, you're the master for this partition of this resource, for example. And you basically just register callbacks, and it takes care of all this stuff. And underneath, it's actually storing everything in Zookeeper. And so like the model I'm actually using is sort of this kind of leader standby. Well, actually, all I care about is I've got partition data, and I just care about the leader, having 1 node that's the leader. And so kind of a simplified form of this state machine. So it kind of, in the cluster, it sort of looks like this, right? Bunch of nodes, bunch of partitions, and replicas, and each one has, on a given machine, has a particular state. So the leader of partition 1 is here, 3 is here, and 2 is there. And all of the other ones are like offline or standby. And then if a machine fails, right, its underlying Zookeeper session times out, Helix just kind of triggers a whole bunch of state transitions, and the nodes get notified to sort of take over from the failed machine. And it has a really horrible API. So just sort of ugly as heck, basically. But this is like how you do the cluster setup, right? So you actually connect to Zookeeper, you add a state machine definition, and there's a built-in like leader standby model. And then you add a resource, so the thing that you want to have partitioned and replicated, tell it the number of partitions, tell it the actual state machine that you want to use. And then you just start a controller. So there's sort of a bunch of different roles in Helix, one of which is a controller that's actually kind of making the partitioning decisions. And what I do is each machine in my cluster is actually both a controller and a participant. But then they do leader election amongst themselves to decide which particular machine is actually the leader for now. And then they fail over. And then you can add an instance, add a node to the cluster, and then you tell it to rebalance that just says, I've added a new node, go sort of move the partitions around to take advantage of that newly added capacity. And then so this is all actually happening in the same machine, in the same kind of, basically I'm just sort of running through the code. And then the other thing you have to do is connect as a participant. And then there's this ugly way of actually setting up the callbacks to get notified, and then you sort of just say connect and get going. So you actually have a factory that creates a callback object. So that's this. So this gets invoked by Helix saying create a new state machine or new state kind of callback thingy for this given partition, and the actual name of the partition is the resource name and the partition number. So you return one of these state model things, and then there's just a bunch of onBecome new state from old state methods that just get invoked to tell you for this given partition what state you should be in. So the big thing is you just define your state machine, you define how you want your cluster partitioned and replicated, you add the nodes, and then Helix just tells the nodes what parts of the cluster partitions they are now responsible for. And so it's an ugly API, but it actually just seems to work. I've been using it for like, I don't know, a number of months now. You can also have the notion of spectators. So these can actually observe, they can actually sort of register with Helix, and then they get notified whenever the state of the cluster changes. So when nodes come and go, they can get notified. So if you had a load balancer, for example, it could be a Helix spectator. And then it's got some other stuff, a property store that's like a write-through cache of Zookeeper data. It can do messaging based on Zookeeper as well. So any questions about that?
Can you ask for more or less replication to get more resilience in the case of something going down?
That's interesting. I think that is fixed, right? There's some cluster some aspects of the cluster, as far as I know, are actually just kind of, you create the cluster and it's just fixed at that point. But one thing you can do is actually just create a highly sort of, actually I'm not, well, well, partitioning is fixed. Maybe you can actually change the replication. I have to go look at the API. It's not as dynamic as I wanted, if I remember correctly. But I figured one way of solving that is you just have lots of partitions, right? And so each machine, you know, it's like if you look at how Cassandra works, I think there's like an awful, you know, there's an awful lot of these little partitions. You know, many more than the number of machines that you have. So you don't have to worry about having too many machines and not enough partitions. All right. So, oh yeah.
So a resource is just something that's identified by some name. I mean, it doesn't know anything about resources, or does it have knowledge about?
No, I mean, it's a totally abstract concept, right? And so, you know, like in the one scenario, there's just the resource is called foo, right? And which pretty much corresponds to, you know, many use cases, I think. But you could imagine just having more, I don't know, you could imagine more complex scenarios, though I'm not sure what exactly. So, okay, so that was Helix. So now you know everything I know about it, which is not too much. And then, so then the other technology I've been using is Kafka, which just seems like this totally cool web scale message broker. You know, the other ones like RabbitMQ and ActiveMQ just seem like so yesterday compared to this, that I actually can't remember how they actually compare. But, okay, so, you know, it's like, it's all to do with messaging. It's, you know, the claim to fame, it's like fast, it's scalable. I mean, I think if nothing else, you know, like, well, many message brokers are fast, and Kafka could very well not, I do not think it is actually the fastest, right? But it's designed to be like web scale. Yeah, so you can have massive clusters. And it's also designed to be durable as well, right? You know, if I think hard, I can vaguely remember, like in some of the other message brokers, like whether or not a topic was durable was this optional thing, right? Whereas in Kafka, messages just ultimately end up on disk. And it's just designed to be like massively distributed. You know, I haven't dug into this, but you can have a Zookeeper, a Kafka cluster, and then you can have it mirrored to some other cluster running elsewhere in the data center. There's just sort of built-in support for that. So if anyone's working with another message broker, it would be interesting to make comparisons. But the big deal is, right, so when you publish a message to Kafka, you're actually, you publish to a named topic, right? So in a way that, you know, that's no big deal. Since with like other protocols, well, you publish to something anyway, like in an AMQP exchange or a JMSQ or a JMS topic. But then where it gets interesting is that a topic is actually a partitioned, well, they call it a partitioned log. So when you create a topic, you actually say how many partitions it has. And a partition is basically this log, as in log, well, I think it's a set of files on disk. So, I mean, I forget the exact relationship between topics and partitions and files and directories, but you can just abstractly think that a topic partition is basically a log, and you're just appending messages to it, and ultimately that gets appended onto a file in the file system. And then messages within a given partition have an offset. So the very first one you write, actually, I think it has offset 0, and the second one is offset 1. So it's just sort of like kind of a counter rather than a byte offset. And then messages are kept in a topic for a certain period of time. Like you could just say for 7 days. I mean, I forget what the default is, but it's just some, you know, it's a long time. And the notion is that, you know, disk space is cheap, right? Relatively speaking, and it can be useful to actually have, to keep messages for some number of days, because you might want to actually go back and process them, right? Go run, like if you're using Spark, or Spark streaming, you can actually plug it into Kafka and then run analytics on the past n days of system activity, for example. As opposed to things living very temporarily inside the message broker, and you have to go get them from somewhere else. You can sort of do more. The longer you can keep things in Kafka, the more you can do with one style of programming. So Kafka is clustered. Each cluster consists of n machines, and each topic partition has some number of replicas. And for each one of those topics, one of the machines is the leader, so that's the one that you write to, and all of the other ones are followers, so slaves. So they actually, so the client writes to the leader for a top partition topic, and then the followers read from the master, from the leader, and actually update their own log. So they sort of, and it's designed to be reliable, and and messages are considered committed when all of the replicas of the leader and all of the replicas are written to their log. Yeah.
The question about the persistence. Is there a notion of like archiving? When you run out of time, the deadline, and things go out of the partition. Can you say I want to archive everything that comes into this thing because I want to replay from the very beginning of time? You know what I'm saying?
I don't think it has kind of an archiving thing, as in if in other words, if something is dropped off the end, put it somewhere else. I don't think you can do that. I would just have a consumer that's actually just dumping stuff into S3, right? So you kind of handle it yourself. There is there's another mechanism, I forget that you can, hold that, I'll say something in a minute. I got to actually talk about another thing. So basically, producers ultimately are just writing onto these replicated log files, and consumers only ever see the committed messages. Though interestingly, with caching done by the OS, just because something is, quote, written doesn't actually mean that it's on disk, right? Physically, actually on disk. And because same is true in databases as well. They don't f-sync as much as you might think. So then on the producing side, a message is actually a key and a value or a body. And what's interesting is the hash of the key determines which partition that message goes in. And you have to, when you're thinking about publishing, you have to think very carefully about what the key should be, right? So if this was a stream of stock trades, you would probably want the key to be the actual ticker symbol of that trade, right? So that because everything in the everything in the same topic partition is ordered, consistently, it sort of makes sense, right? Because if you had some other key, IBM trades could end up spread across multiple partitions, and you actually have no meaningful ordering on them. And then the publisher has to talk to the topic partition's leader. Client side, the client's kind of interesting. It's actually very different in as far as the server doesn't keep track of where a given consumer, of what messages a given consumer has actually read, which is quite different, I think, from a lot of other message brokers, right? So basically, the underlying protocol for the client is, okay, I'm going to read for this given topic partition, give me the messages starting at offset n. And so the server will just give you that. It doesn't care whether you've seen them before. And it's basically the client's responsibility to actually keep track of the offsets of the messages that is actually consumed before, that is actually processed. So that's very different from a traditional message broker. And this side of things, this part of Kafka is pretty ugly, because there's a really simple Kafka consumer that gives you a lot of control, but then you have to deal with figuring out for a given topic partition what the leader is, tracking the leader when it changes because of a server failure, and also actually store the offsets. Yeah.
So, please correct me if I'm wrong, but so far I'm getting that for every partition, you have a number of replicas, right?
Yes.
And if you read something from one of the replicas,
Well, you always read from the leader, right?
you read from the leader, but okay, and those replicas are just for redundancy if the leader.
Yeah. So if the leader goes away, the assumption is that one of those will become the leader, and then producers will write to that. Consumers will read from the leader.
So when you're reading from the leader and you're storing or committing the offset at the leader, you don't need to bother copying the same offset to all of the replicas, right?
Well, the server doesn't track what offsets you have read. Basically, the client has to maintain a database of, for this topic, this partition, I have read up to offset n.
So if the master for that topic dies for some reason, and the next master is elected, you will need to communicate that offset to.
Well, you just start reading from that new leader, right? Using the offsets that you have. So there's a low-level consumer that kind of just really exposes the underlying mechanism. Then there's a high-level consumer which actually does all the offset tracking for you because it actually stores them in Zookeeper. But then what's really annoying is that, and it also hides all the leader stuff. You just connect, what's really annoying is that if it gives you a message, it basically assumes that you have processed it and will not give it to you again. There's some sort of subtleties to it, but it's basically a hugest pain in the butt because you can't. Because really, when you process a message, you then want to say, okay, increment the offset by 1, right? But it's basically, if you read it, you've processed it. And but there's a new consumer coming, which is good. Where the next release, I think, is going to have a much better consumer that gives you a lot of flexibility. So you could store the offsets in DynamoDB, for example. So it kind of ends up being your job, it sort of hides the complexity of leaders and, but gives you the flexibility to store the offsets how you want. Once again, it's got a really ugly API. Like you create a consumer connector, and then you create these message streams where you actually pass in a map saying, for this topic, I want to have n streams back. So I'm going to have the model is so for every topic you have one or more streams, and for each stream you have a thread. So that's sort of how you achieve parallelism inside your consumers. Right? So if you just want to have one thread, then you just basically would pass in a map of the topic name and 1. And then, so you get back a map from topic name to a list of streams. So if you said integer n here, you will get back n streams. And then from the stream, you can get an iterator. So it's got a pull model, which is kind of annoying, actually. So you have a whole bunch of threads just pulling, basically calling next on the iterator, and it can time out where it has next, while it has next, next sort of kind of pattern. So you end up with just a bunch of threads in your app just pulling data out of Kafka. And because of this stupid problem with offset processing, there's even uglier stuff going on that I'm not going to talk about. But anyway, so Kafka is truly web scale, right? Like, I mean, these numbers that from LinkedIn are just sort of like mind-blowing. Yeah, wow, seriously. And of course, we all have problems like this, so it's a really good fit for our companies as well. But at least it, it demonstrates that it works. And even though it's sort of rough around the edges, particularly with the consumer stuff, though, maybe if I went back and looked at, now that I have experience with it, if I went back and looked at the low-level consumer, I could probably, I'd probably would use it now. But I'm just figuring the new consumer in the next is going to come in the next release. But so it's a fascinating product. Anyway, so summary, they're really cool. You should use them. Then you can be like LinkedIn.